Okay, we're going to do section 6.4, at least the first part. I've done the two examples on a part B. Okay, so here's 6.4. We're going to talk about the central limit theorem. So consider a problem like this. This is the kind of problem we've been doing in like section 6.3. If you look at this, we got a rugby team. Single randomly selected rugby players. I want the probability that the single person's weight is greater than 200 pounds. So I would set it up. My mean is 208. That's my mu. Sigma, standard deviation is 34. 200 is over here. So this problem's looking for that area. I'm not going to do the problem for you, but I will give you the answer. 0.5948. It's good practice for you to do that problem. Now, what's different with the central limit theorem? Instead of looking at individuals, we're going to look at samples. And here it is. So we want n to be greater than 30, or we'll see there's another criteria that we'll talk about. And what's going on is in 6.3, we talked about the sampling distributions of means of X bar. Now we're going to use it to do problems that involve samples. And when we do it, everything's going to be the same. We're going to have the normal distribution. In here, we're going to have mu. You're going to read about this notation. The mean of the sample distribution. Well, central limit theorem says it's the same as the mean of the population of individuals. So we got this in here. Okay, we also have the standard deviation that's associated with the sample distribution, and that's the big change. It's our regular standard deviation of our population, but now we divide it by the square root of the sample size. And that's all that changes. Remember when we did sampling distributions, we talked about samples of size n are selected from the population. When we were trying the bears, we were trying samples of size 20. Now I want to look at these requirements before I do one problem for you. If n is bigger than 30, we're good to go. Notice when I said the mean of the sample distribution is the mean of the population. Standard deviation, well, we end up dividing by square root of n. And our z-score changes because this just goes in the denominator. Now, if n is not bigger than 30, we need to assume that our population has a normal distribution. Now, that's kind of a big assumption, but look at the problem that I'm going to do next to finish this section. Going back to rugby players. Notice what I put in here. The weight of rugby players is normally distributed because N is only 15. Okay, so N is less than 30, so we fail that criteria. But because I said it was normally distributed, the population, we're okay to go. We've met that criteria. So how do we set this thing up? Probability that 15 randomly selected rugby players have a mean weight of more than 200 pounds. I'm going to draw the same picture I always draw. Just a second here. I thought I could insert a page. Maybe not. I'm looking for more white space. Come on. Oh, okay, I'm just gonna have to do it right here. I set it up. Okay, the mean, 208. I'm looking for probability that now my 15 rugby players have a mean weight greater than 200 pounds. Because if they have a mean weight of more than 200 pounds, 200 times 15, that's over 3,000 pounds, the deck is gonna fail. Okay, so here's the big change in these problems. My standard deviation is different. Sigma is now, great, can't remember the 34 pounds divided by square root of 15. Okay, now I'm going to find my Z. Unfortunately, I'm going to have to erase here. Z will be negative because it's to the left of the mean. So my new Z score, 200, subtract 208, divided by 34, that's the standard deviation of the population, divided by the square root of the sample size. I get negative 0.91. I'm going to let you find the area, however you want to do it. But I get 0.8186. That's the probability that the mean weight of my 15 rugby players is greater than 200 pounds. That's pretty high probability. So we go back and say, pretty good chance that our deck is overloaded because the mean weight of the 15 people is greater than 200, multiply that by 15, and you are going to be greater than the 3,000. So that's what central limit theorem does. You can read the rest of this section or go through this PowerPoint. I do the two examples in the other video, section 6.4b, that's already been posted.